Okay, so I'm Rick Grandy. I've been doing VFX for about 25 years. Started off doing matte painting and modeling and shader development, and then kind of moved into pipeline technologies, workflows, ways to essentially make the creative process more efficient and better for the artists. I've been at NVIDIA for about 8 months, and one of my focuses is on looking at AI and how we can bring that technology into this content creation workload. So the first thing I want to do is I want to kind of talk a little bit about what we mean by AI and deep learning. So AI is kind of a catch-all for basically having machines do stuff for you, from playing chess to driving a car. Machine learning is a subset of that, where computers are given the ability to learn without being explicitly programmed. In other words, we're letting the computers learn how to solve those problems. Neural nets are one branch within that. It's kind of a deep learning function which is set up to work the way that our brains do. We're basically creating these neurons and connections between them, essentially passing data back and forth and making associations. Deep learning is a further subset of machine learning, but it focuses on basically deep neural networks. The idea of, rather than just doing one or two operations, we're stringing a whole bunch of stuff together, computing a whole bunch of data to solve much more complicated problems. So what we're doing is we're setting up kind of a whole new computing model. Like the traditional model is essentially, you take someone who has a lot of information and a lot of knowledge about computer vision, and they're going to write a specific application that knows how to look for the edges of a car and look for the headlights and look for the wheels. And after a few weeks or a few months of coding this up, they're going to have something that can recognize a car, and it works great on a car. And then someone gives them a motorcycle and it doesn't have 4 wheels, and they've got to redo the whole process over and over again. And it gets a little tedious. Deep learning, the basic idea is we want to present the computer with the examples of what something looks like, or what something sounds like, or what something is, and have it learn what those appropriate traits are and to find them and to do stuff with them going forward. So we could pass it an image of a car, or we could pass it an image of a motorcycle, and as long as I tell it this is a car and this is a motorcycle, through the experience of thousands and thousands of images of training this network, it's going to learn what the differences are. It's going to figure out what are the features that are most important for defining this, rather than me trying to define those features itself. So we're not going to go deep into math or anything, but I'm going to do kind of a quick overview of kind of like the deep learning process. And the biggest thing that I want you to take away from everything is that deep learning is really about association. So if you're doing something like labeling data, I need to know that, well, this picture of a cat, I need to know that's a cat. If I'm trying to do, say, super resolution, I have a low-res image and I want to turn it into a high-res image, I need a high-res image and a low-res image that correspond to train the system on. So it's all about that association. And those associations can be anything. We can talk about images to images, we can talk about images to audio, you can text to image, all sorts of different ways. So we have our inputs, and that could be, audio, video, texture information, and we have our outputs, like we're going to get something out of this. And the biggest thing we want to figure out is, well, what is the question that we're asking for this particular process? So I have a list of a bunch of things. Is it present or not? What type of thing is it? What is the likely outcome? And that kind of breaks it down in what are these predefined tasks that are pretty common within deep learning: detection, classification, segmentation. So a lot of this we can look at like just doing face detection within a scene. It's kind of like detection. Is it present within the scene? Classification. Well, what type of face is it? Whose face is it? Segmentation. Where within the scene is it? So when we talk about deep learning, we also need to break it down into 2 major components. There's training and then inference. So training is essentially taking a whole bunch of data, giving it to a model, and having it make associations so it knows what to do with it. Inference is actually taking that model and putting it to practical use. So I've taken 20,000 images of cats and dogs, trained a model, and then I want to be able to pass it to something, and then I want it to instantly tell me that this is a cat, this is a dog, this is a cat, this is not either, something like that. So we start with that training data set. So essentially we have to collect as much data as possible. And this is usually the hard part within most deep learning pipelines, is actually coming up with the appropriate data set. If we're only classifying, say, cats versus dogs, all we need are images of cats and dogs. If we need raccoons, we add raccoons into the picture. Next thing to do is we have an untrained model. So essentially, this is kind of a neural network that has a whole bunch of what we refer to as layers. So you've got your input layer at the top and your output layer at the bottom, and then a bunch of what we'll refer to as hidden layers in the middle. This is a very simplified network that we're showing, but essentially a deep neural network could have tens or even hundreds of layers depending on all the different operations or algorithms that you're going to run on it. And it could be chopping, dicing, matching, you name it. So we find a framework. You basically pick your framework: Caffe2, TensorFlow, MXNet. For those of you who are jumping into deep learning, NVIDIA, on our developer portal, we have this thing called NGC, which is our cloud. But essentially, it's not really we call it the GPU cloud, but we're not like offering cloud services. What it is we're offering Docker containers, which have an entire environment set up for you to basically kind of hit the ground running. So rather than you spending 2 weeks trying to figure out what libraries or what versions of random esoteric things you need in order to get your first demo thing running, you can basically go in and say, I want to use TensorFlow with Onyx, and download a container, and it'll work just for you. And the cool thing is you can do 20 different things, each with their own container. You don't have to worry about having clashing environments. So that's a really powerful thing. But anyways, back to this. So we've got we basically pick our framework, and we stuff all our data through that framework, and we train our model. And we end up with our trained model. Ta-da! So the next thing is the end result is usually you need to build an application. So what might take hours, days, or even weeks in order to train this model, the idea is to build an inference engine so that you can take this and have an application that will feed it new data, and that new data is going to be compared within the model, and it's going to give it that end result. Is this a cat? Is this a dog? Is it neither? Is it a raccoon? So there are a ton of different neural networks out there, and this was a snapshot of some of the common ones that I took a few months ago, and it's probably tripled in size just in the past couple of weeks. But there are a few ones that are a little more popular that I want to talk about a little today: autoencoders, deep convolution networks, and generative adversarial networks. Again, this isn't going to be a very deep talk, so I don't want to get into the math and technical details of a lot of these things. I went to art school. I'm not capable of half of it. But what I want to go through is this is going to be kind of more of an inspirational talk. There's a lot of research that's being done at NVIDIA and also by universities, production companies, and people kind of around the world that are just kind of lurking at what the possibilities of this thing, that's somewhat new on the scene are. And for me, it's really exciting because, not that I want to say that development within visual effects and graphics were stagnant, but the last 15 years, there hasn't been a giant incremental leap. And we're just now starting to see that again. So it's really exciting just to see, what is possible. And there are things that are already released on the market, and there are things that people are actively working on. So this was experimental a couple years ago, but now it's actually reality. So what are the useful things that we can do with deep learning besides, labeling? We've discussed that, but we want to go into something where it's actually more useful for production. So we're going to talk about denoising. Denoising is something that is very popular within ray tracing these days. It's kind of like the holy grail for computer graphics. Ray tracing replicates how light behaves in an environment. It's a technique used to create images for broadcast feature films, everything you guys know about. And even with the advancements in hardware and software over the past 20 years, it still takes hours or even days to render a high resolution final image. So when we're asking about making ray tracing faster, what we're trying to do is we're trying to resolve that final image faster. How can we get there with a fewer number of samples? So denoising is something that we've released as part of our optics framework. So essentially we have an optics SDK, which includes our path tracer, which is being utilized by a lot of the rendering companies out there now. But there's a separate API in there for denoising. And the truly great thing about it is it comes as a pre-trained model that you can basically run on its own and denoise your images. So kind of you can render within one renderer, and you can use this denoiser on those images. Essentially what it's doing is it's trying to figure out from thousands and thousands and thousands of images, what those correspondences are. So we took a couple thousand 3D scenes and we rendered, tens of thousands of images out of it. And within each of those images, we saved off different sample points after 2 samples, after 4 samples, after 8 samples, all the way to a ground truth. And I think Ankit was telling me it was 130,000 samples. So that we had a completely noiseless image, which is ridiculous, but that's what we rendered to. So now we have that association, noisy, clean. And now you can apply those inference, and the inference is milliseconds. So we can, in your interactive workflow, you're sitting there and you're looking at something, and sometimes it might be hard to judge the shading or the overall texture of something, with the noise in there. And with the denoiser, you can turn something that used to be, hit a button and wait experience into a more interactive experience. In a lot of cases, we're seeing a 10x performance speed up in basically a result-oriented task. So that's all fine and good if you're sitting there and waiting, but everyone is looking at real time now. So in a lot of cases, essentially, we're looking at doing real time, whether it's for location-based entertainment or games, cinematics. So what we want to do is we want to say, well, it's great to wait a few milliseconds for something off of something that took a few images, a few minutes to render, but can we ray trace complex scenes in real time? So what we're looking at here is the result of path tracing every single pixel, 4 samples per pixel. Now, this is kind of what you can do in real time. Not exactly a final image, but can we do something in order to take the limitations of ray tracing and accelerate it? What can we do in order to make it good enough, essentially? So we talk about selectively ray tracing. So when you look at the contents of a scene, when you're looking at a flat shaded wall and you're looking at certain things, not everything really needs to be ray traced. So it's kind of like, what are we going to get the most bang for the buck? So we took a look at 3 specific areas: ray trace shadows, ambient occlusion, and reflections. And we applied denoising techniques to them. So we'll start off looking at ray traced area light shadows with denoising. So why did we pick shadowing as one of those areas? Well, it's a lot more physically correct than map soft shadows. There's a very distinct difference that you can see. I'm just going to go to show it. So there's a distinct difference between looking at a mapped shadow and a ground truth rendered shadow. So this is kind of like the end result that you'd want to get fully ray traced to a ground truth. And this is what we get with 1 sample per pixel. But we can denoise it. So what we can render in milliseconds, the ground truth versus a completely clean and denoised image. Other area we looked at is ambient occlusion. Same type of thing. There's a lot of discrepancies between screen space ambient occlusion versus a fully ray traced ambient occlusion. One of the big things being that stuff that's outside of the scene, outside of the frustum of the camera, isn't taken into account. So we can look at the example of screen space ambient occlusion versus the ground truth render ambient occlusion. It preserves a lot more of the high frequency detail. And the contact regions between objects are a lot clearer. We can create, a 2 sample per pixel pass on the whole frame and denoise it. We achieve, again, very similar quality to that is attained by, our ground truth. And the last area I want to talk about is reflections. So ray trace reflections are actually the most diverse of all of them, mainly because of the orientation within screen space. Basically, rather than having a pre-generated environment or basically reflecting something that's flat, you're actually getting things that are reflected from their true depth within space compared to the objects they're reflecting on. So we have an example of screen space reflections versus a pretty big difference when we ray trace those reflections. Our ground truth, it's going forward on me. So 1 sample per pixel will denoise to that. The ground truth, and then looking at that again. So I think we answer the question, you know, with hundreds of samples of pixels generally required for achieving that final result, can we get that result with 1 to 2 samples per pixel with denoising? Yes, if we're selective about it. So I'm just going to skip ahead. So within this, essentially, we've created this stack called RTX, which is our ray tracing technology. And I don't know if any of you have seen it, but we've created a demo video that shows off essentially the features of NVIDIA's RTX. Essentially, RTX is a rendering framework that's available through optics. You can access it in a number of different ways, but coming soon, it's going to be an integral part of many of the game engines that are being available for virtual production and live events and cinematics. So I want to show this really quick.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector. If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What? You think she heard us? Yeah, I think she heard us. At least we blend in for once.
So that was a collaboration between Epic, NVIDIA, and ILM's X Lab in order to basically prove the point that it is possible. And now I want to talk about super resolution. So while what they do in Blade Runner or in CSI is a little outside the scope of what's possible, there are some things that we can do in order to use autoencoders in order to learn more about the composition of shapes and objects within images in order to upscale them in a much more believable fashion. So in particular, we'll go with a couple traditional techniques using like a bilinear upscaling. You can really see the aliasing around the headlights and the lack of clarity in the logo on the white disc there. And if it moves forward. So here's a bicubic interpolation versus the deep learning version. Inference time is a few milliseconds. So the idea is to be able to take not just final images, but taking texture libraries, and being able to upres textures from old content into new content. There might be applications where you want to actually stream lower res data and then actually upscale it in real time. So there's a whole bunch of different applications for essentially what we're doing, here on still images. Like you can apply it to video. If you basically add a bunch of layers to give you temporal consistency, and then there's style transfer. A lot of you have probably seen the demos where we can show, we're live video running and we'll turn you into Picasso or a Van Gogh painting, but we want to show a variation on that. This is something that we call fast photo style. And essentially it takes two images. Given a content photo and a style photo, the code transfers the style of a photo to the content photo. So if we have a content photo and a style photo, we get an end result. So looking at use cases for this, think about style, being able to come up with different art styles for a commercial, or when you're looking at location scouting, being able to see what something might look like, at a different time of day. that actually gets us into Moonit, which is this new style transfer system that we're coming up, which is I'm going to read this. It's a multimodal unsupervised image-to-image framework. Basically, it not only takes the picture of something, but it also takes into account the style of it. So if you take a picture of a cat, the pose that the cat is in is the content, but the breed of the cat is a style. So not only can we just say, change parts about it, we can completely change, say a cat into a dog or a cat into a lion. So some examples that we have are essentially, given the input of a couple shoes, we can make lots of variations on those shoes. Given some handbags, we can make variations on those handbags. For the idea of being able to build out worlds where you need to create lots and lots of variations, you can have your texture artists come up with a few key variations to define that style. And then you can basically go in and you can create a whole library of things that match within it. It's also useful, as I said, for doing things like, I want to see what something in winter looks like in summer. This new multinodal system also gives us multiple end results. So we can see multiple variations on, what the sky would look like, or different foliage on the trees. And kind of going the opposite, we can add different levels of snow on that. This has lots of those applications, especially you're looking at like, location scouting. You go out and you see what something might look like in the in the dead of summer, but you might have a few shots where you need to see what that's going to look like in wintertime. You can use techniques like this to do a really quick pass to get approval from the director before you send your map painter down the road of creating that final product. It gives you that initial jumping off point much quicker. Okay, so now I'm going to talk about something that I find a lot of fun, face swapping. There's been a lot of talk about deep fakes and things out there, and there's a lot of things that you can do with it. There's been a lot of content generated with it, and there's a lot that we can be using it for specifically within content creation and production. What I want to talk about here is it's also a really good example of the fact that within doing this one task, there's a lot of different answers that we have to these questions. So essentially, we need to find a face within a frame. We need to make sure we're finding the right face, and we need to crop down to that particular face, and we need to know what is its orientation, and then we need to match that with another actor's face, and we need to determine what is the most likely image that's going to match that one particular frame. Again, it's all about the data. If you go in and you have just a bunch of random pictures of a celebrity off of the internet, you might not have a great set of data. But in the cases of the productions we're working on, I could have a stunt double, on set doing some work, and I can totally capture everything about there. And I have that lighting environment. I can bring my principal actor in that same lighting environment and go through a kind of like a fax range of motion within that lighting environment. I can have them say some simple dialogue, and I can use that direct training data. So now I have a direct correspondence of two faces in the same environment, and I'm going to have the system train on those so that I can basically match the proper orientation. And the great thing about it is I'm going to get the reaction time of the stunt double. I'm going to get that real emotional impact that they're going to have when they're smashed in the face applied to Nicolas Cage. But I'm not going to smash him in the face.
First I was afraid, I was petrified. Kept thinking I could never live without you by my side.
This is not Nick Cage.
But I spent
This
so
is
many
Amy Adams.
nights just thinking how you did me wrong. But I grew strong, and I learned how to get along.
So that's our source image. So we've got this video of Amy Adams singing better than I can sing. And we're going to use an autoencoder to essentially find out what that difference is. Autoencoders are really good at basically feature matching and extraction. So in this case, we are going to create a series of matched images between Amy Adams and Nick Cage. It's going to look for, as I said, things like orientation, lighting, mouth shape. And this is where the difference in different networks are going to be. Like, you can find a generic network out there. Like, you can go to deep fakes online and you can download their network. They might not take into account all of the features that you want to take into account in yours. And that's why being able to take that neural network and add those convolutional layers to look specifically for the features that you want it to attract. Like, lighting might not be a concern for you. You might want to take that out or add it in. but we want to swap their faces.
You're one, now go. Walk out the door. Don't hang around here, 'cause you're not welcome anymore. Aren't you the one that tried to hurt me with goodbye? You think I'd crumble? You think I'd lay down and die? Oh no, not I. I will survive.
That was done with found footage. So it was an interview of Nicolas Cage sitting in a chair giving an interview on like the Dr. Oz show. And there are some issues with the final composite. Essentially what it's doing with their feature extraction, part of it is also creating a matte for areas that they think are, have the highest, level of recognizability, like, the eyes and the mouth, and they do soft blends elsewhere. But there's nothing that says you can't do the full face. Like in most cases, you probably wouldn't want to blend features to features. And that goes into modifying kind of like that end result of it's outputting, the matched face and then also an alpha matte in order to do that automatic masking. Like I would do an end result where I'd actually output those two things independently, and I would actually rewrite the convolutions for how it's determining that face and write out a better matte. And essentially you give those to your compositor to clean up, and then you can have something that's going to be a dead-on match. So what can we do with this? So we talked about stunt head replacements. Also limiting reshoots. I mean, essentially, if you've got an actor like in that space and they're delivering, dialogue, you've got that whole set to train on. You can basically retrain it against new dialogue. So these days, when reshoots happen, sets might not exist. It's really hard to find studio space right now in order to shoot in Los Angeles. So it's kind of a premium thing. So if you can go in there and you can present, your client with an ability to have them go in and ADR some new dialogue and be able to limit that amount of reshoot time, and you can basically reanimate to it auto-magically, that's a huge win. We talk about insurance and liability. If an accident happens on set and there's, there's an injury to a performer that might not easily be covered up by makeup, this is something that you can do in order to keep the schedule still on budget. There's a lot of work in I'll say enhancing features of certain performers as they get older. So within that whole realm of digital cosmetics, this is a great application for that. We say adjusting extras that stick out. There have been some situations recently because of the global nature of where production is going. A lot of times, the representative crowd of extras that are used for a particular environment doesn't match the end resulting city. We had an example recently where it was shot in Atlanta, but it was supposed to be in San Francisco, and they wanted to basically change the ethnic makeup to have more of an Asian mix that they didn't have with their shooting group. With this, they were able to do that. They were able to go in and basically come up with the mix that they thought was appropriate for the scene setting within the film. Also, this isn't limited to live action shoots. If you're doing something like I'll say like Benjamin Button's, in which they had a younger or older version of a particular actor, you could do a CG head and you could render that head. Essentially think about rendering out a full phonetic range and expressions within a lighting environment that you captured. You capture the HDRs on set already. You can light your younger version of that character that you've created and essentially create this range and then do the same thing. Have it determine what are the features that are going to match to your performer to make them younger or older. And then you give it that leg up when your compositor goes in and marries the two performances together. So next thing I want to talk about is locomotion. Essentially, we've talked about things that we can do within a 2D space a lot of times, but there's also stuff that we can do in a 3D space. So my notes don't make sense. Okay, so there have been some papers that have come out around deep learning for locomotion and a whole bunch of different things, and one that we're going to focus on is actually referred to as a phase function neural network. And it was developed by a group at the University of Edinburgh, and it's kind of become a pretty big kind of thing, within the gaming community, looking at ways to get more realistic motion through the existing data sets that they have. So this is an example of a character that's basically built around a game controller. So rather than going in and creating tons and tons and tons of cycles and having an animator laboriously change between, what the character is doing, essentially they have a whole bunch of motion capture data of someone like walking, up ramps, down ramps, jumping on and off objects, and it's trained against all the other possible actions that are required. Essentially, this is a kind of a multi-network system where we take in 3D skeletal data, the animation that's being captured, and as long as you capture the possible actions that you want, like you want to make sure the character looks right jumping off of a cliff, get them jumping off a cliff, or climbing a rope. So then we need to go and we need to label the data. So we need to know because this is going to do transitions based on, the speed in which the character is going. Essentially, when the motion vector changes, it needs to know how to go between a walk or a run. And it also needs to know what phase it's in. Essentially, like if you're in the middle of a walk, you don't want to rewind and start the beginning of a run. You want to make sure that your foot is continuing forward on that path. And you need to know what the footstep positions are. So this thing trains that data against what we call fit data. So essentially, we know the pose of the character. So if you look at all these different images, the pose is essentially the same, but there's a whole bunch of different ground terrains that basically fit that data set. So since the terrain is a key factor in this kind of, where are you going, what's your motion in the last couple of frames, what does the terrain look like under you, then we can determine or predict what that next possible pose is going to be. And so just kind of like looking at the face functional neural network, that's what it's doing. The final inferencer basically is going between multiple neural nets, and as the function changes, it's figuring out which one it needs to utilize a pose from. So we can look at all the inputs and outputs. We've got our joint positions and our velocities. We know what it looks like on the previous frame, and we're looking for that same thing on the output. So as long as we have the trajectory where they're going, we know the direction, and we know the height of that terrain, we're all good to go. So here's an example that we've taken and we've actually implemented it as an inferencer within the Unreal Engine. So we can retrain it on our own motion capture data, and we can basically have a character that walks around based on our own environment with our custom model. We can also write this so it can take advantage of the GPU, and we can get over 500 characters walking around in real time. So when we're looking at advances in crowd systems, being able to do something like this and being able to present a result on basically, the sparse population of a city is really hard for a director to gauge whether or not you've got the layout that they want. But if you could do something like this and have the characters actually moving realistically without having to worry about hitting a button and coming back the next day, you can get much faster feedback and iteration. The idea being you can do a format like this, almost like scene planning and layout, and then you can go in later and you can call out the particular characters that are going to need special attention because of their distance to camera or particular motions that might be called out. But that system doesn't really adapt to change very well. If you think about it, it's essentially a pose switcher. Everything you motion capture, you have available. So if you're walking on flat ground, you've got that. If you're walking on a 25-degree ramp, you've got that. If you're walking on a 12-degree ramp, you're kind of in trouble. So what you can do is kind of a bunch of different things. One thing that's done a lot in video games is you put like an IK system on it. So essentially, you know what the ground is going to be, and if you're not reaching the target ground, you basically can pick another pose, or you can have it decide, well, if the ground is lower than me, have the IK adjust the position of my foot so it's actually on the ground, or adjust it up so it hits the ground. But what if we could train the network to actually learn to work in a physical environment? So this is where deep locomotion comes in. So rather than working on basically having something that switches between different variations of motion capture, we want something that's going to take the physical properties of an environment and learn within that. So we can train something to walk and locomote and move based on the environment that's giving, and sometimes it works well and sometimes it doesn't, and we can make it robust or not, and we can give it a lot of different conditions. We can have it not only walk but kick a soccer ball, achieve this end goal, avoid these obstacles, and you can get great results for like path planning and really figuring out your scene. But there's one big thing about this is it all looks like robots walking around. So the next thing we need to do is we need to make it look real. So some of the research we've been doing on is actually combining these results. So when you look at the deep locomotion thing, essentially it's reinforcement learning. So essentially every time that it achieves a goal, it knows like, that's good, that's what I want to do. So if we tell it stand upright and walk forward, and it walks forward. And if we say stand upright and walk forward and make sure that you've got this type of a step timing, we can give it all these various goals. What if we add to that goal this PFNN, this phase function motion capture data that we have this huge library for? So now we can basically say, not only do I want you to like stand up and walk from point A to point B on this terrain, which you're going to automatically adapt to, I want you to have the characteristics, the style of this other motion. So we essentially, while the phase function neural network isn't going to be physically accurate to the environment, it's going to know what to do based on what it learned on terrain through your motion capture session. So we give this as another goal for this reinforcement learning. And what you can see here is the fact that we can do this on tens of thousands of essentially brains at one time. And we run an iteration, and essentially you go through and you take the brain that produced the best result, and then you copy it back out to all 10,000, and you run it again, and you copy that out to all 10,000, and you run it again. And that's how you can deep learn at scale. This is how you can train robots to do things in a virtual environment, so that when you release them in a real environment, they know how to react to those changes. They can, you're not, from a safety point of view, it's not going to learn on its first day. It's going to have years worth of training within an environment with people before you even release it on the factory floor. And this I like showing because it's just a lot of fun. This is like my kids in preschool. Each of these characters has a goal of getting up and running and either tackling or avoiding being tackled. So, but this is entirely learned behavior through those simple set of goals. I can watch this all day. Performance capture. This is something that's kind of pervasive and getting kind of more and more detailed throughout all aspects of media creation. So in a traditional sense, there's a lot of work going on and basically trying to reproduce the performance of an actor. Setting up in front of like a multi-camera rig, capturing that performance in video, somehow transferring that performance to either mesh per frame or some other way of driving it, putting it onto a rig, whatever, and then you can solve that and you can use that data in your application, whether it's real time or rendered. The problem is it's not always that reusable. You're capturing specific actions that might be very specific to that one target in time, that one performance. But what if we wanted to do something a little different? What if we want to take a performance and we don't want to just play it back, we want to actually learn from it? So we actually did a research project with Remedy, and we trained a neural network to directly move the vertices of a face. Initially, the traditional way, we capture the video, and we'd have the video basically, drive a vertex-based solver, to move the positions of the face. But then we also trained that end resulting data against the audio. So the end result is that we can change the audio and have the audio drive the appropriate lip sync. And if you have enough training data, you have various intonation changes that might express different emotions, you can actually pull out an emotional content from the audio as well. This will play. Oh, I guess I got to build it up. Okay. Oops. I just want to play the video. It's an awesome video if it plays. I'm going to do it the other way. If I turn off presenter mode. Is it playing? It's playing for me. Sorry, let me see if I'll just drag the whole thing over there. See all the secrets. So what you can see here is essentially like the original data that was captured and the data that was utilized from that initial capture, video-based, retargeted onto onto the mesh. And then the final one on the right-hand side, that's an audio-based inference of it. So essentially, this particular audio was not used for the training. So this is an inference of that audio being played back, in real time. So some of the key things that we can do with this, which if you mixed a bunch of different techniques, you can do an audio-based performance where you can get full expression on a video-based performance, or you can get full expression on the face, the blinking of the eyes, the furrow of the brow, the true emotional content of the character. But then if you did an audio-based, you can relocalize for multiple different markets. So you've recorded it in English, and then you can release it in French, you can release it in Spanish, you can release it in Japanese. A lot of that emotional content, the overall expressiveness of the face is not going to change from language to language, but the lip sync will. So the audio-based lip sync in combination with that kind of gives you the ability to localize. It also gives you the ability to essentially release the characters without doing any hand animation on them. So if you spend all of your work and you build a training set on your hero characters, you have something you can learn and train from for your background characters. So now you can release background characters for video games or within your crowds, which you might not have had, the time or the budget to animate before. You can train on the data that you've needed to create for your hero characters in order to create those performances for your background characters. And again, relocalize them, deliver game content without any facial animation keyed in, deliver it to each market with the audio. The audio will automatically drive the performance of the face. And this is ongoing research that we have going currently. So, and now I want to take questions. Thank you.
My question is for when you were talking about cell transfer, especially face swap.
Mm-hmm.
So when you have two characters, the source character and the destination, the best way to train the network is to use the same, let's say, this faces and snapshot and frames from the same performance, or would you mix it up? Let's say if I have Nicolas Cage, would you take Nicolas Cage from the same interview, or would you try to have Nicolas Cage from many movies so that you get different lighting?
Well, kind of depends on what you want. So like in that result, because I'm basically inferring something within one particular environment, I want the lighting that matches that. In theory, what I'd want to do is like that, you would train it against like your two sets of images, one being the source. You could basically use like, well, this is the video that I'm replacing. So that will be one side. And the other one, you want to have something that as closely represents the things that you can't control. Like essentially it's going to go in and it's going to, match the lip sync. It's going to match the orientation of the head. But if the lighting is completely different, then it won't match. If you do have something where, say, you're doing this on a feature film, essentially you have all of the data that was captured for a particular actor, all those different lighting environments, all those different scenes. And if your neural network is taking lighting into account as one of the factors to do the face match, then it will find the right one from that huge data set. The larger your data set, the larger it's going to take to train. So on a data set like that, you can train like that face swap data set in a few hours on a single GV100. If you wanted a full data set that was, of higher resolution, that was, YouTube 720p quality. If you were basically going to have 2K or 4K data sets to train from, you're going to want to have something that's going to be able to handle the buffer size, the memory that required, and go from there. But yeah.
Thank you.
Mm-hmm. Next.
You're saying that the resolution is affecting the calculation, but could you have the result on a lower resolution and apply it to higher resolution?
You can apply super resolution to it. There's a lot of people looking at a mix of combinations in order to be able to accelerate getting results for dailies. So you can look at rendering lower res, interpolating every other frame, and then using super resolution and frame interpolation in order to basically create your finished, product. For getting lighting buy-off, that might be the great way to go. There's a trade-off that you get with, using, denoising and super resolution. And one thing you can even do is you can even train specific to your use case. Optics ships with a generically trained denoiser, which works really well on almost all renderers, even though the noise patterns of the path tracers are different. But if you needed to do something that was particular to an environment, like if you're working on an animated film, you basically might want to go in and say, I've got these 3 major environments. Here's, in the dungeon, here's out in the field, and here's in the hallway. And you render representative images of those particular environments, and you can train a denoiser that's custom to those environments, or you can augment a generic training set that you might have. You might have 10,000 images that you have. This is my base training set. And then I have these 2,000 images that I've rendered of this particular environment that I will augment and retrain. So now I have a dungeon-specific training set. So.
Can you expand more on building neural networks, and how do you like put stuff that you need and remove stuff you don't need on the existing templates?
So basically, you can. I can't go too far into it. But basically, if you think of it like you're writing code, it's a series of layers, and within those layers you have the nodes. And so what you're trying to do is you're trying to go through, and there's within the different frameworks you have the ability to go in and actually see what the connections are between those nodes. And if you're familiar with coding like convolutions for like Photoshop filters or something, that's largely what you're doing. Is you're basically telling it what types of features or the ways to segment the image, or what types of things it's going to look for in order to go beyond that. No idea if I'm answering your question, but I guess the big thing is we have a ton of information on our developer blog, and we actually have something called the DLI, the Deep Learning Institute. So if you go to NVIDIA.com and you look up the DLI, we have a lot of courses, and a lot of them are free, that go through the basic fundamentals all the way through training you how to do from the ground, network setup. So you can kind of like take that whole thing. We also offer courses to companies that are looking to do kind of like more of a deep dive, an accelerated deep dive into deep learning. We can come on site and we'll give you a course on specifically like, auto encoders and use of GANs, using, I think there are companies that are using cycle GANs specifically for removing facial capture markers, and so that you can then retrain on the non-markered footage. So now you have a more of a real world environment that you can train against. So being able to reuse your data is something that's pretty key. And also there's a big push now about synthetically generated data. Daniel Holden, who did the phase function neural network paper, he's this year released a paper on motion capture cleanup. And rather than going back and looking at all of the positional markers and the fluctuation, how bad they were, they started with their final clean data. They took the clean data, they put a rough skin on it, and they essentially interpolated, the positions of where all the markers might be, and they wrote an algorithm that kind of generated noise. Some markers, switch places or just like randomly move off in space or have some noise in it. And they trained a whole thing on motion capture cleanup without having to actually go back and look at the marker data. It's all based on their clean data. So synthetically generated content is a big thing, as long as you've got, that end result. You can do the same thing for, say, denoising sensors. You can take clean images that were shot with a particular camera, and you could run it in a nuke. And if you can synthetically generate or apply noise that you captured over black or something that's related to, the ISO of that camera, you can apply that over an image, and you can train it. Now you can train to remove it. So you can basically do, high ISO shoots and remove some of the grain, in a much more naturalistic fashion. So DLI, check it out. It's awesome. I go there every day. Any other questions? Yeah.
Resolution-wise, when I dived into neural networks recently and do some exercises, and usually the batches of images are very small, 32 by 32, 64 by 64, and so on. Those results that I obtained, let's say, doing some segmentation on a 64 by 64, they cannot be applied on a HD or 4K image, or can they? Or do I have to train a network with 4K training set in order to transfer it?
Most things actually break down to the fact that you're doing segmentation. So you don't generate or look at the entire image as a whole. So, but when you're looking at setting your batch sizes, memory is like your key. So with a lot of these things, like there's a couple universities that are doing training for video-based inferencing, and they can't train on anything more than 720p on their GeForce cards. GeForce cards are great for some playback in certain situations, but if you need that large frame buffer, a 32 gig card, or our DGX stations, which have 16 of those in NVLink as one giant memory space, you can train on 4K data and larger batch sizes. The big thing about the batch sizes, it's not a linear thing. It's not like I have 2 GPUs, so it's going to be twice as fast. 2 GPUs with a shared memory space could be 4 times as fast or 5 times as fast, depending on what you're doing. So we're talking to some people about like the broadcast space, being able to do all of your work, off of your existing 1080p cameras, and then rather than having 4K cameras for everything, have 1K camera to do a representative shoot of the event, like say a half hour before the event, capture 10 minutes worth of footage, and you got to train that footage fast. But you train that footage on a DGX station, you can train 10 minutes of footage. Okay, well, it'll take about an hour to train 10 minutes of footage for super resolution on a DGX1, but you could then upload that model to your broadcast site. So now you can do all your work locally like you're currently doing at 1080p, and the broadcast site can now put full 4K at broadcast time.
In terms of hardware planning, in 5 years, is GPU, CPU going to be, are we going to see another division because of deep learning, or is NVIDIA going to make?
I have a big bias.
Yeah.
So, but a lot of it kind of like looks at what your application is going to be, and the biggest thing about like our current set of cards, the Volta cards, is the fact that we actually have implemented tensor cores within the chip. So specifically, it's a part of the chip that's specifically designed just for doing inferencing and training. It does these matrix multiplication operations, in a blink of an eye. So in like the phase function neural network demo we showed, the idea is you're not using your CUDA cores or you're not using your CPU, which is important for other aspects of the game. You could do the full inferencing of the character on those, on those cores. I think there is going to be a big shift. Like right now, deep learning is one of those things that works great in parallel. You've got huge data sets that you're doing these associations, and the parallel abilities of the GPU are kind of geared specifically toward this. You can do it on a CPU, and a lot of it comes down to, well, how much time do you have to wait? That's kind of like the big trade-off.
If Python becomes multi-threaded, and things like PyTorch kind of are in competition with TensorFlow, do you see that at all happening in the near future?
Well, at the end of the day, it kind of depends on what part you're looking at, because it kind of doesn't matter for the training and the inferencing, because like we're already accelerating all of those networks. So if you get our Docker containers, so we've accelerated every major framework specifically for being parallelized on the GPU. And one thing we also have is a thing called TensorRT. When you're looking at the inference side, I've spent all this time training the model. You spend all the time training the model, you want the highest quality model you have. So you're going to train it with, like full float, you get the data down. But then when you're running the inferencing, we've done a lot of tests, and sometimes you can degrade that data to like half float or even int8, and you get nearly the same result. So what TensorRT does is it kind of looks at your network, and it looks at, well, what are the things that are actually contributing to the output? What are things that I can, combine? It simplifies your network layer, and it allows you to change between like your FP32 all the way to FP16 or int8, and it does that in seconds. So you can have your full model, and you can look at what your release structure is. So if you're going to release something for a video game, the memory size required for that model for int8 is going to be much smaller. And if your results are 99.7% the same, it's probably going to be okay. So, but yeah.
One last question.
Okay.
In that slide where you had like weather lighting conditions from one frame of the building from another point.
Mm-hmm.
Is that going to be through a specific software? Like through what means not accessible to artists?
Well, there's a lot of stuff right now that you'll actually find, like we have GitHub repositories for a lot of the stuff, so you can check it out. So depending on how tech savvy you've got it. We have a lot of partnerships with a lot of the software vendors. We do a lot of work with kind of all the major ones, Adobe, Autodesk. And some of them are starting to be released, as I said now, Blackmagic has a super resolution. They call it super scale. They don't advertise it as being a deep learning based super resolution system, but it's in there. It's in Resolve right now. Things like the style transfer. There are things that I know some of the other vendors are working on that I can't disclose, but the idea is yes. We're looking at releasing SDKs and frameworks that help accelerate other people's software development, like we do with optics and like we do with other aspects of GPU rendering. So, thanks everybody.